So dear friends, now let us start transmission lines. Actually, in electrical engineering, two-wire transmission lines, that means two conductors. So this is one conductor, this is second conductor. So in electrical engineering, two-wire transmission lines are used to transfer electrical power from one location to other location at low frequency called 50 Hz frequency. So same two-wire transmission lines are used in electronics and communication engineering to transfer power at high frequency, that means greater than megahertz frequencies from one location to other location. So maybe in electrical engineering or maybe in electronics and communication engineering, these two-way transmission structures are used to transfer power from source to load. Source is at one location, load is at other location. So let us write the statement. In electrical engineering, two-wire transmission line, no, short name is TX line, we will write. Two-wire transmission lines. So in electrical engineering, two-wire transmission lines are used to transfer energy from source to load at low frequency. Example, at F is equal to 50 Hz. Example. Okay. In electronics and communication engineering, two-wire transmission line, or otherwise transmission lines, two-wire transmission line is used to transfer energy from source to load at high frequency, that means frequency is greater than few megahertz. For example, radio mirchi signal 98.3 megahertz, like that. Okay. Now, if you see this diagram, actually here a message signal is there, Emft. So for example, here one person is talking, and that person is talking, then message signal comes here, message signal. Okay, message signal. Now this message signal is through the conductors, it is given to the modulator. Okay, and here FC carrier signal generator is there. Carrier signal generator is there here, dear students. Now, for example, FM signal modulator is there. So the modulated signal, already you know all these concepts, no? Because this is low frequency, it cannot be transferred for longer distances. So if you want to transfer for longer distances, you have to put that message signal on the carrier signal. So carrier signal has more power, it can carry for longer distances. So here in the modulator FC carrier signal, this message signal is inserted onto the carrier signal in different ways, by changing amplitude or by changing phase, etc., etc. So here now you have high frequency modulated signal is there, and these are two-wire transmission structures here. And if you want to send for longer distances, then you have to put here amplifier. Okay. Now again two wire conductors are there, first conductor and second conductor. Now here they are given to the antenna. Okay. This is for example transmitting antenna. Dear students, once if it is transmitted into the air, it is transmitted into the air medium like this. That is called uniform plane wave. Uniform plane wave. If it is transmitted into the air medium, you see here, this is a high frequency signal is there, FM signal here, and this one and this one, they are actually, I will write here, they are actually maybe two wire transmission line if frequency is less, or otherwise coaxial cable, little high frequency. Further high frequency, then it is wave guide. So actually here a signal is that high frequency signal is passing through the two conductors from one location to other location. If frequency is very high, we will send through coaxial cable. Further very high frequency, gigahertz frequency, we use wave guide actually. Because if frequency is very high, signal come out of this conductor, and that is why in the waveguide signal is transferred from one location to other location, not through the conductor, between the conductors it is transferred. Anyway, we will discuss all those things. Now what chapters we study? Whenever EM wave comes out of the antenna, then it travels in the air medium, that is called uniform plane wave chapter. Here some radio will be there, then this signal is received by radio antenna. So that is antenna chapter. How much transmitted from the antenna, how much received from the antenna, that is antenna chapter. That is one chapter. Then here at very high frequency, the signals are transferred using waveguide. That is one chapter, waveguide. Now at low frequencies, this signal, high frequency signal, is transmitted through the two-wire transmission line. That is this chapter. So that is why I told you, whatever signal, for example, radio Mirchi signal is transferred here through the two-wire transmission line, then same signal is radiated into the air. That is why in uniform plane wave chapter, whatever equations come, similar equations come in transmission line also, because whatever signal is transferred through the transmission line, same signal is radiated by the antenna and same signal is propagated in the air medium. That we have studied. Uniform plane wave means how EM wave travels in air medium or otherwise dielectric medium, etc., etc. we have studied. So that is why in the transmission line also, in the waveguide also, in the uniform plane wave also, concepts are similar. Because everywhere they have to carry the power. If air medium is there, then power is carried using electric and magnetic field. And here two wire structures are there, then power is carried using voltage and current waveforms. So in the two conductors, power is carried through voltage and current waveforms, because through the conductor current can be carried. So here now in transmission lines also power is carried from source to load using two conductors in the form of voltage and current. The same voltage changes to electric field if it is radiated into the air. Same current is same current. This current in the two-wire structure changes to magnetic field in the uniform plane wave. Now, dear students, here What is the transmission line? First of all, you have to understand that. What is the transmission line? Transmission line is pair of conductors. That means two conductors. First conductor like this and second conductor like this. They are the first conductor and second conductor. Why two conductors? In one conductor, current goes from source to load. In other conductor, there should be a return path. That is why two conductors. Next, what is the input to the two-way transmission line? Then answer is it has to carry the, for example, FM signal. Then this is called FM signal generator. And according to network theory, every signal generator or otherwise every signal source has voltage and internal impedance. Voltage and internal impedance. Then the signal present in that signal generator is supplied to the two-wire transmission line, first wire and second wire. Then it is supplied to the transmitting antenna. So antenna is one device. Every device has input impedance. For example, transistor is one device. Transistor also has input impedance. So similarly, antenna is one device. Antenna has input impedance. The input impedance of this antenna conductors is load impedance to this transmission line, because this transmission line is feeding the signal to the antenna. So that is why transmission line load impedance is equal to the input impedance of this antenna. So dear students, transmission line is nothing but two parallel conductors, and the input is, example, FM signal generator. Every signal generator has internal voltage and internal impedance. Now, the load impedance to this transmission line is input impedance of the antenna. So, now we are going to, what do you say, I have drawn this diagram. Now, I will be explaining you how this first conductor or otherwise the second conductor, how they behave whenever high frequency current or otherwise high frequency voltage is transferred through that conductor. And from that we are going to discuss transmission line parameters. Okay, so here I am writing transmission line parameters. Okay, now consider one conductor. This is actually conductor, this one. Out of two conductors, this is one conductor, one more conductor will be there. I am discussing the behavior of this conductor. Automatically bottom conductor also behaves in same way. Now let us say this conductor length is L. Now the area of this cross-sectional area is equal to A. Then that conductor has sigma. You say sigma C. Sigma C means conductivity of conductor. Sigma C. Sigma C means conductivity of conductor. Why I am using C? After some time we will see medium also is present. Medium conductivity is there. I will call that as a sigma M. So sigma C is conductivity of the conductor. Okay. Now if I send current, DC current, I is equal to 6 ampere, then that is actually DC current. Frequency is 0. So this DC current is transferred, 6 ampere current is transferred in entire area. पूरा एरिया में जाएगा वो, ऐसा जाएगा, पूरा एरिया में जाएगा स्टूडेंट्स, पूरा एरिया में जाएगा वो, ऐसा जाएगा, पूरा एरिया में जाता रहता है. लो फ्रीक्वेंसी करंट utilizes the total area of the conductor. Now, so that resistance offered by this conductor is equal to rho L by A, or otherwise L by sigma C into A. Here sigma C is very high, so that is why this is approximately neglected 0, because sigma C is very high. Okay, this is neglected for normal cases. But same, I will write this as a case 1. So that case 1 is how this conductor behaves whenever a low frequency current is transmitted. Now case 2, student. Case 2. Here let us send I of t is equal to 6 sine or otherwise cos any signal. So sine omega is 2 pi f. Let us send 10 to the power 8. Frequency is now 10 power 8, 2 pi f t. That means you are sending the frequency, high frequency signal here. So frequency is 10 to the power 8. So this is a high frequency signal we are sending through the conductor. Now what happens if you send high frequency signal? Here this is the conductor. Okay, it is observed that this conductor has length L, of course sigma C only conductivity. Here A is area, or otherwise this is also called physical area. I will write here. Now it is observed that whenever frequency is very high, DC means continuously constant current is going, disturbances are not there. That means ups and downs are not there. In the conductor, disturbances are not there. But AC signal means positive cycle, negative cycle, high current, low current, high current, low current, lot of disturbances are there. So that is why this conductor cannot handle the disturbances. Then this conductor tries to send that signal out of the conductor. Then it goes, that current goes only near the surfaces only. It goes only near the surfaces, high frequency currents. So that high frequency current only goes here like this. It goes only near the, okay, only near the surfaces it goes. Even if current is very high, no, dear students, then what will happen? It comes out of the conductor. Okay, it comes out of the conductor. So that is why transmission lines cannot be used at very high frequencies, because transmission line conductors themselves radiate electromagnetic energy. So these transmission lines, if you send very high frequency signal and they themselves radiate here itself, they cannot supply energy to the antenna, because the antenna is a device that only radiates EM wave efficiently, and also before what do you say, radiating, it has to amplify also. But if you send a very high frequency gigahertz signal through these conductors radiate that energy here itself. If you send gigahertz signal frequency, even they can't carry the that signal to the amplifier. So here itself radiated. That is why these two-way transmission lines are not used at gigahertz frequencies. Then we have to use waveguides for that. So waveguides are used at very high frequencies. That is why they are called high pass filter. And these two-way transmission lines are used to transfer energy from DC frequency to up to hundreds of megahertz. That is why they are called as low pass filters. Actually, they can't carry the power at very high frequency because of radiation losses. I will write these points in the rectangular waveguide chapter while explaining the difference between two-way transmission line and the rectangular waveguide. Anyway, now here the area utilized by this current is only A dash. So here A is actually A is physical area of the conductor. A dash is area used by high frequency area used by high frequency current signal. Okay, dear students. Now here resistance R dash is equal to L by sigma of the conductor into A dash. So here wherever current goes, that area you have to write. So here A dash is much less than A. So implies this R is there na here. R. Okay. R dash is much greater than R. You can see now here in R denominator area is there. That area value is more, but here A dash value is very less. That is why R dash value is much greater than this R. So this R is what resistance offered by the same conductor at low frequency. R dash is resistance offered by this conductor at high frequency. So here R dash is resistance offered by conductor at high frequency. So R dash here it is approximately 0, R dash not 0, so R dash cannot be neglected, dear students. But here R can be neglected because sigma c is very high and area is also very high, denominator very high, so numerator becomes 0. But here sigma c is high, but A dash drastically reduces, that is why it is less value in the denominator. So R dash value will be high, you can't neglect that. That means whenever you send high frequency currents in the conductor, that conductor at every location the area is decreased. So at every location it offers resistance. So at every location means distributive. Distributive means at every location it offers resistance. Then for each meter length, how much resistance is offered by that one. That is why here transmission line parameters are always measured per each meter length only, because sometimes we use a long transmission line. Then for total length, resistance calculation is meaningless. It won't give any meaning. If you calculate per meter length, then for example, resistance is equal to 5 ohm per meter length is there. Then automatically for 10 meters, how much resistance is there means multiply with 10. That is more meaningful. Some other person uses 11 meter transmission line, then resistance offered by 11 meter is equal to 5 into 11. That is more meaningful. That is why here transmission line parameters are calculated per each meter length. So now this resistance is called series resistance. Series means parameter, that is resistance parameter, is produced due to the current going inside the conductor or through the conductor. So parameter is produced due to the current going inside the conductor or through the conductor. Then that parameter is called series parameter, dear students. Okay. Now if any parameter is produced due to the, this is first conductor, this is second conductor, if any parameter is produced due to the medium, here air medium is there. Some cases dielectric medium can be put here, like wood material you put here and do the packing. Then between the transmission lines wood medium is there, that is dielectric medium. So if any parameter is coming due to the medium present, for example here wood is there, any parameter is coming due to the medium present between the conductors, then those parameters are called parallel parameters or otherwise shunt parameters, they are called as. Okay, so now in the transmission lines, so transmission lines means what, student? Top conductor is there like this and bottom conductor is there like this. Both are of same size like this. Both are of same size. Okay, like this. Now this conductor also, actually what happens if you connect some voltage source V of G here. G means generator here, and this is ZG, and this is the structure. I told you this is nothing but the equivalent circuit of FM signal generator. High frequency signal sources are called here generators. So this is internal voltage of the FM signal generator and the internal impedance of the generator ZG. Now this high frequency signal is given to the two conductors here. Then this is the load impedance. This load impedance is nothing but input impedance of the antenna, actually. Input impedance of antenna. Now whenever high frequency current goes through this I of t, then that goes here again, it comes back. So in both conductors that current travels, so both conductors offer resistance. Then after manufacturing, what they do by doing experiment, they measure per each meter length, 1 meter length, how much resistance is offered by both the conductors. That is symbolized as capital R. So capital R is a series resistance of both conductors per each meter length. When these transmission lines conductors are manufactured, they do the experiment at particular frequency, and on the data sheet, they print that information. So as an engineer, you can go and see that data sheet, and whatever resistance value conductors required, you can pick up that one. कोई बात नहीं, वो सब practical aspect जरूरत नहीं है. So dear students, now let us write first parameter, that is capital R, is called as series resistance of both conductors of transmission line. Series resistance of both conductors of transmission line per meter length, that is ohm per meter. Okay, next, if the transmission line conductors are perfect conductors, so that sigma c is equal to infinity, then resistance is equal to L by sigma c into area. So if this is infinity, then you get 0, resistance 0. But dear students, this is only theoretical discussion. You can never get perfect conductor. So that is only theoretical discussion. That is not useful discussion. Then as an engineer, you can select best conductor. For best conductor, sigma c not 0, but very, very high. So denominator very high, and then resistance not 0, but very less you get. So if we select best conductor, that means best available conductor in the market, then sigma c is very high, so that R is not 0, but very less. Because in denominator very high, then numerator very less will be there. It is not 0, it is present, but less value is there. That is the statement. Next, here L parameter is there, inductance parameter. L, dear students, L. So L is series inductance of both conductors per meter length. So series inductance of both conductors per meter length. So that is Henry per meter. Why inductance comes, dear students? For example, here in this first conductor also current is going. Then what do you say? Here ZL is there. So in this also current is going like this. Current is going. Okay. Now current is coming out. So whenever current goes, what will happen? For example, current is going like this. Then magnetic field is produced here like this, no? Magnetic field H bar is produced. So like this, H bar is produced in both the conductors. Here it is like this, H bar is produced. So because of this H bar, now already we have seen some students, gate students, they might not have seen the static magnetic field, but no problem. So magnetic field half Li square, because of inductance magnetic energy is stored. So whenever there is a magnetic field, inductance parameter is calculated. Whenever there is an electric field, then capacitance parameter is calculated. Whenever heat losses are there, then resistance parameter is calculated. Because conductors offer very high resistance for the high frequency signal. So that is why heat loss is more. That heat loss is represented in the form of resistance parameter. So here in this conductor also current goes, that generates magnetic field. In this conductor also current goes, that also generates magnetic field. And this also has inductance, this also has inductance. Wherever magnetic field is there, otherwise wherever current is there, half Li square, then magnetic energy is stored. So here also current, here also current, then both will have inductance actually. So that is why this inductance is coming, why this magnetic field is generated? Because of current. Where current is going? Through the conductor. I told you, if any parameter comes because of current going through the conductor, then series you have to say. So series inductance of both conductors, in both of them current is going. So otherwise both of them current is going, both of them generate magnetic field, both of them will have inductance. So per meter length. Now third parameter, student, C is a shunt or otherwise parallel. Shunt capacitance of the medium. Where is that medium? It is present between conductors per meter. So I will show you here. For example, this is one conductor and this is the second conductor. Here load is there, ZL. Here for example some voltage source is connected like this. Then here positive for positive charge, here negative charge is there. So this is the medium. I told you it can be air medium. If you want to fill up any dielectric, you can fill up dielectric between two conductors like this wood material, and this is some dielectric. Do the packing here, do the packing, so that then if you do the packing, then between the conductors this dielectric medium is there. So it can be any medium. Now that medium has a epsilon parameter. So now electric field goes from positive to negative. I told you if electric field is there, then that is nothing but voltage half CV square. Capacitance parameter comes. That capacitance parameter is calculated for this medium which is present between the conductors for each meter length, because at every location, at every length medium is present. At every location positive negative comes. At every location electric field exists. So at every location capacitive effect is present. So that is why it is called a distributive parameter. So that capacitance is coming because of medium present between the conductors. Between the conductor means that is shunt or parallel connection actually. So shunt or parallel capacitance of medium which is present between the conductors now per each meter length. Okay. Now for example we have seen for coaxial cable this is inner conductor and coaxial cable this is outer conductor. If the medium is epsilon and this is A radius, this is B radius, then capacitance is equal to we have calculated 2 pi epsilon h divided by ln B by A we have calculated per each meter means h is equal to 1. So 2 pi epsilon divided by ln B by A capacitance per meter length is there for this. Like that here also formula is there. We will talk of that later on. Okay. So see shunt or parallel capacitance of medium present between the conductors per each meter length, dear students. Now fourth parameter G. Okay. As an engineer, we think that this medium should have zero conductivity. So why zero conductivity, dear students? For example, if I am sending here 10 ampere, I will draw the diagram here. So if I am sending here some 10 ampere current, for example, if I am sending here 10 ampere current, student, I will expect here also 10 ampere current. When that happens, when there is no current leakage here, then here also 10 amperes come. Then if 10 ampere is here, if here also 10 ampere is coming, there is no current leakage, then the conductance of this medium is 0. So, but no dielectric medium is perfect. Perfect means we expect for dielectric medium sigma is equal to 0, but generally every dielectric medium has a very small value of sigma. The practical value is 10 power minus 17 mho per meter conductivity is there. That is very small. That is why leakage value also very small. So for example here current leaks here, current leaks let us say point point. So dear friends, let us start the static magnetic field chapter. Actually DC current produces static magnetic field, or otherwise magnet also produces static magnetic field. Now let us study the equations of magnetic field due to DC current. So if you want to have a current, then there should be a conductor. So let us take one conductor here. In this conductor, this is a conductor. In this conductor, I1 current is going, let us say. Now because of this current going in this conductor, around this everywhere, for example here there is a conductor, in this if I current is going, around this magnetic field is generated, and in that magnetic field you can calculate magnetic flux, you can calculate magnetic field intensity H bar, and you can calculate magnetic flux density B bar. You can calculate energy stored in the magnetic field, you can calculate inductance. Those things we are going to calculate in this chapter. Now at point 2 location, around this, let us select this location, that is called point 2. At this location you want magnetic field intensity H bar, you want H bar here, that is called field point, because you are calculating the magnetic field intensity at this location. Now somewhere here origin is there, because these points are located with respect to origin. Here O is origin. Due to I1 current going in long conductor means source length is more, then magnetic field produced is H bar. Due to the I1 current going in small length vector called dl bar, differential length vector, wherever you select this differential length vector, that is called as point 1 location. That means at point 1 location you have selected a differential length vector, so we are calling it as dl1 bar. So differential length vector at point 1 location. Due to I1 current going in small length vector, then differential magnetic field is produced. That means small amount of magnetic field is produced. This is symbol is once again I am telling, if I1 current goes in long conductor, then more amount of magnetic field is produced, that is called H bar. If I1 current goes in small length vector at point 1 location, then differential magnetic field intensity is produced. The symbol is dH bar. Now here OP1 bar is positional vector of point 1 with respect to origin, OP2 bar positional vector of point 2 with respect to origin, then R12 bar is a distance vector from point 1 to point 2, that is point 2 minus point 1. This is in point form. In position vector form, OP2 bar minus OP1 bar. So here this is a unit vector A R12 bar. Unit vector in the direction of R12 bar is R12 bar divided by modulus of R12 bar. I am calling this simply as A12 bar, because every time difficult to write R1 to R12, so it is A12 bar. A12 bar means unit vector in the direction of R12 bar. So once again I am writing here DL1 bar is a differential length at point 1. If you multiply with I1, then that is called differential current element at point 1. Element means length, differential element means small length. In small length current is going, so that is why it is called as a differential current element. At which location it is present? At point 1 location. Here point 1 belongs to source. Here source is current. That current is generating this field. That field is called result or otherwise cause. Effect. This is the source or otherwise cause. This causes, that means that is responsible, current is responsible to generate the magnetic field. So this is called result actually. So DC. So if we select best dielectric, then for that best dielectric, students, sigma of the medium is approximately 10 to the power minus 17 student. This is value. Then G not 0 but very small, because if sigma m 0, G 0, but sigma m is very small, then G not 0 but very small. Now R, L, G, C parameters of transmission line. First one depends on conductor dimensions like area, etc., but independent of length. Why independent of length? Because we are calculating per each meter length. That is why per meter length we are calculating. That is why depends on conductor dimensions but independent of length, because per meter length we are calculating, students. Second one is it depends on the type of the conductor. Depends on type of the conductor. Depends on type of the conductor. That means whether it is good conductor or perfect conductor, like that. Then also depends on medium present between the conductors. Depends on medium present between the conductors. For example, student, G and C parameters are calculated for medium, and R and L are calculated for medium. For example, resistance is 0 if we select perfect conductor. Resistance is not 0 if we select the best conductor, that is type of conductor. Then they depend on area of the conductors, that means dimensions, but independent of length, because what do you say, we are calculating these parameters per meter length, that is why. Okay, now let us write, here I wrote note, you read this one. Let us write transmission line equivalent circuit. Transmission line equivalent circuit and transmission line equations. We write these transmission line equations very logically from network theory. Actually, these are all derivations. I told you derivations are not at all useful for examination. After derivation, whatever formula you get, we have to remember that formula. We have to remember that terms, statements in that formula. What is what, you have to remember. Then you should solve the questions. So then you will get the best rank actually. You do all unnecessary derivations, and then anyway, I will be doing some derivations to get the continuity in the concepts actually. Okay. Now transmission line equivalent circuit and transmission line equations. First, let us draw the equivalent circuit of the transmission line. I already told you transmission line has first conductor and second conductor, like this. So total 2 conductors are there, like this. Now here signal source is connected to this, like FM signal generator. Every signal source has a internal impedance called ZG, generator impedance, then voltage of the generator is there. So G means here generator, student. You can, if you want, you can write. I am not writing. G means generator. Now here we will be connecting load impedance ZL. That load impedance is nothing but input impedance Zin, input impedance of antenna, because we are connecting that to antenna. ZL is equal to Zin, that means input impedance of antenna, because these conductors carry high frequency energy and they supply that energy to the antenna. The antenna input impedance behaves like load impedance to this one. That is why simply we call it as a ZL from now onwards. Let us assume these conductors. Let us assume these conductors. 2 conductors are there. Here 2 conductors are there, like this. First conductor, second conductor. Here we are connecting the source, and here antenna conductors are there. That means here source is there. Here signal is carried in Z direction like this. Now even if we turn the conductors like this, we can take that as a Z direction, because I told you we always do the derivations and write the equations by assuming wave is traveling in Z direction. In the uniform plane wave also, in the transmission line also, in the waveguide chapter also. If wave travels in Z direction, you always get terms like e power minus j beta z like that. So let us take this is Z direction, az cap, Z direction. Let us assume wave is traveling in Z direction. Now this one is what, dear students? Starting distance z is equal to 0. Now if you say total length of the transmission line is capital L or otherwise small l symbol also used, capital L also used, it doesn't matter, where L is length of the transmission line. Now Z0 means starting distance, that is nothing but sending end or otherwise source end, SENDING. Sending end means here we are sending the signal from source to the transmission line. So this is called sending end or otherwise source end, where distance is 0. Now if you go from here, that small z variable is used. Z means distance from source end. Z is equal to 0 means at the source end, Z is equal to L means at the receiving end, or otherwise it is also called load end. So it has two names, sending end or otherwise source end. This is called receiving end or otherwise load end, because at this location signal is received from the two-wire transmission line. So that is why it is called receiving end or otherwise load end. This is called sending end or otherwise source end. Now Z0 means at source end. At some distance called small z, you go to some distance. There you select a very small length called dz or otherwise delta z. So delta z or otherwise dz. So this delta z is a very small length. For delta z distance, this conductor and this conductor both have R into delta z ohms resistance, because capital R is resistance of both conductors per meter, and this is ohm per meter. You multiply with delta z, then you get this is ohm. Delta z means overall you get impedance ohm. So R into delta z ohms resistance is there for both conductors for delta z distance, that is series parameter. So now I am starting here, I am drawing the equivalent circuit here. For how much distance I am drawing equivalent circuit? Only for delta z distance. Now once again, in the equivalent circuits, it is shown like this, dear students. It is shown like this. So this is here Z0. We are not drawing equivalent circuit here. Now you go to Z distance. That means from here to here you go. Here we are drawing the equivalent circuit. For how much distance? For delta Z distance we are drawing. So I am enlarging this delta Z so that we want to write something. ये delta Z को बहुत बड़ा कर रहा है, क्योंकि इधर लिखने के लिए लिखना है, कुछ लिखना है, इसलिए इसको बहुत बड़ा कर दिया. सच में वो बहुत छोटा वैल्यू है डेल्टा जेड. सो फॉर डेल्टा जेड डिस्टेंस both conductors have R into delta Z resistance. So R into delta Z ohms resistance is there, because it is ohm per meter, and this one is delta Z is actually ohm. So you get these many ohms. That is series resistance. बॉटम कंडक्टर में जितना रेजिस्टेंस है, टॉप कंडक्टर में जितना रेजिस्टेंस है, डेल्टा जेड डिस्टेंस के लिए दोनों को जोड़ के ऊपर लगा दिया, फिर इधर नीचे लगाने का जरूरत नहीं है, वो सीरीज पैरामीटर है. सिमिलरली top conductor, bottom conductor together have L Henry per meter. You multiply, this is Henry per meter, you multiply with delta Z, then that is meter. Ultimately meter cancel, so you get these many Henry's series inductance. That is why it is written here like this. So L into delta Z Henry series inductance is there for both conductors, so that is why it is series parameter here. Now for delta Z distance, here medium is there. That medium has C capacitance per meter. If I multiply with delta Z meter, then I get C into delta Z farads shunt parameter, that gives parallel connection between top and bottom conductor. So shunt parameter, that is shunt means, dear students, parallel parameter. Okay, so C into delta Z farad, that is shunt parameter or otherwise parallel parameter. Similarly, this medium has G mho per meter conductance, multiply with delta Z, that is meter. So these many moles are there, that is once again shunt conductance that gives connection between top and bottom conductor. So that is why top and bottom conductor connection is given here. So that is actually G into delta Z. I can write this delta Z sometimes small z or capital Z, you don't bother, students. Delta Z or capital Z. If you want, you can write small z only, or capital Z also written, doesn't matter. Don't confuse. Sir, कुछ जगह में छोटा, कुछ जगह में बड़ा, doesn't matter, students. Z is Z only. So this is mho. Now, for example, इधर तक है वो, up to this na, this is delta Z distance. I enlarged this. Actually, this is delta Z tends to 0, but if I take very small, I can't write this. That is why I enlarged. Now, can you tell me what is this distance, dear students? This one. This is Z plus delta Z distance. This one. This is Z distance. This is 0 distance. Z distance. Z plus delta Z. This is. And I will draw like this if I want to write something. So this is the what do you say, equivalent circuit for how much distance, delta Z distance. I told you voltage and currents, na? Voltage and currents come in the network theory. In the network theory, you can't take distributive parameters. That is why again you came ohm, and this is Henry, and this is mho, this is farad. Okay, no problem. What is the heading actually? Transmission line equivalent circuit. So this is the equivalent circuit for delta Z distance. The delta Z is selected at Z distance from the sending end. So it has a series resistance and series inductance and parallel conductance and capacitance. So this also comes in objective question. Which of the following is the equivalent circuit of the transmission line? You tick mark this one. This is the what do you say, correct diagram, right? Now you want to write transmission line equations. What do you mean by transmission line equations? On the transmission line, what is the voltage equation and what is the current equation? Definitely they should be similar to the uniform plane wave electric field and magnetic field equations. They are second order differential equations. We will see, we will talk of them. Now, on the transmission line at z distance, students, here na, at z distance, here A hai wo z distance, but place is not there, I am writing here. So at z distance, current on the transmission line is called I of z function of time, and at z distance, voltage on the transmission line is called V of z, that means voltage at z distance function of time, like this. Now at z plus delta z distance, the current is I of z plus delta z distance current, it is a function of time. Similarly, voltage at z plus delta z distance, it is a function of time, like this. Now if I want to write voltage equation, I am using shortcut method. If I want to write voltage equation, here voltage is V of z comma t. Here voltage is V of z plus delta z comma t. I am saying here if 10 volts is there, definitely here less than 10 volts should be there, because in the series elements there is a voltage drop, that is why. So conclusion, on the transmission line, if distance increases, voltage decreases because of series elements. 1 point over. So that is why whenever I want to get the transmission line voltage equation, then I have to use series elements. Next point. For example, here let us say 3 ampere current is there at z distance. Definitely here current should be less than 3 amperes because some current is leaking here, so that current is less here. Why current is reduced on the transmission line if distance increases? Because of shunt parameters, or otherwise shunt elements. That is why whenever I write the current equation, then I will take shunt elements actually. So now I am going to write the transmission line equations using shortcut method. So here first I will write the voltage equation. Which equation? Voltage equation. So first one is voltage equation. Okay. On transmission line, voltage decreases with increase in distance because of series parameters. So that is why one series parameter is R and other series parameter is L. I will take this as a current I of z comma t, and I will take this as a voltage V of z comma t. Okay. Then if current goes like this is plus minus plus minus. Students, actually you know what is the derivation, what is the actual derivation? You will be applying a KVL, KCL equations here. Then in the mathematics, Maclaurin series, Taylor series is there. Through that you have to, using Maclaurin's and Taylor series, you have to expand the equation and substitute delta z tends to 0. Then you get voltage equation. But without doing all those things, using our common sense, we are writing the voltage equation by taking series elements. R comma L are series elements. Now let us say total voltage is V of z comma t here, and the current through them is I of z comma t here. Now let us write the voltage equation. So total voltage in both of them, V of z comma t is equal to voltage in this plus voltage in this. So V of z comma t is equal to voltage in this is R into I of z comma t plus here voltage in inductor is L into di of z comma t divided by dt. This is network theory actually. In the network theory, this is ohm, and this is Henry. Am I right? Then this is voltage. So this is correct in network theory. But in EM theory, this is meter per meter. Actually, R is series resistance per meter length. L is also series inductance per meter length. So that is why here per meter should come. Then the effect is dou by dou Z, because per meter is there. We are writing for delta Z distance. That delta Z is nothing but dz here. The meaning is for small distance dz or otherwise delta Z, there is a small change in voltage called dV. That is the meaning of that. And here minus sign comes. You know the reason. Minus indicates that for delta Z distance, the voltage changes, that too that is decreases. Minus means decreases, because series elements no voltage decreases. That is the meaning of that. So this is the voltage equation in the time domain. Now, minus dV by dz is equal to R into I plus L into di by dt. So dear students, already in uniform plane wave we have seen here z is there, differentiation time is there, two parameters are there. If two parameters are there, means two independent variables are there, it is difficult to solve that. That is why we go to phasor domain or steady state domain. In steady state domain, d by dt is replaced with j omega, then only dv by dz will be there. So it is if single variable is there, then it is easy to solve that one. So this is time domain. In phasor domain, this equation becomes dVs. Vs means voltage in steady state, minus dVs by dz R into Is. Is means steady state current. L into d by dt j omega Is. Is means steady state current. So in the phasor domain, phasor domain or otherwise steady state domain, equation 1 becomes minus dou Vs by dou Z is equal to R into Is plus L into j omega into Is. So dou Vs by dou Z is equal to minus of R plus j omega L is common, Is comes, that is written as minus Z into Is. So dou Vs by dou Z. So this is equation number 2. Here Z is equal to R plus j omega L, these many ohms per meter, because here R is per meter, L is also per meter, that is why you got per meter. This is called as a series impedance. Series impedance. Series impedance. Okay. And anyway, you remember this equation, Z is equal to R plus j omega L. Okay. Right. Now, let us write the current equation. Current equation on the transmission line. On the transmission line, current decreases with increase of distance due to shunt elements. So that is why these shunt elements are actually R in simply you write R, network theory model we are writing, and C. So here let us say this is I of Z comma T, and this is V of Z comma T among through them voltage. Now here this I current is divided into resistance as well as capacitor in the current. This current is divided into resistor and the capacitor. Now total I of z comma t is equal to g. No, this is student, not this is a print miss. This is g actually. Okay. So V by R gives current. 1 by R is G. So G into V of Z comma T is current through this. Then I is equal to C into dV by dt. So C into dV of Z comma T divided by dt. I told you this is the network theory equation. It is correct equation whenever G is in mho and this is in farad. But in the transmission lines, this is conductance per meter length, this capacitance per meter length in the transmission line. That is why here per meter should be there. So here actually that is dz. The meaning is for delta z or dz distance, there is a change of current di. Current change is there. That too, that decreases actually because of losses in the loss of current in the shunt elements. And this is the current equation. So this is equation number 3. If you remove them now here like this is the current equation actually. So if you want, you can write them for your convenience. Now this is in time domain. In phasor domain or otherwise in steady state domain. So in phasor domain, equation 3 becomes so phasor domain equation 3 becomes, this one is minus of dou is steady state current, dou z g into V of z comma t voltage time domain is written as Vs plus C into this is d by dt j omega and Vs. So dou is divided by dou z is equal to minus of g plus j omega c, g plus j omega c Vs. So that is dou is divided by dou z is equal to minus y into Vs. This is equation number 4, where y is actually g plus j omega c per meter should be there. Per meter, mho per meter, because g is 1 by meter, mho per meter. This is also per meter is then capacitance. That's why this is called shunt admittance. Shunt. So you put this in the box, dear student. If you want the voltage equation of the transmission line, you need one differential equation. In the differential equation, both sides voltage should be there. If you want the current equation on the transmission line, you need one differential equation. In that both sides current should be there. Here there is one differential equation, but one side current, other side voltage, so it is not suitable. If you want to solve the current equation on the transmission line, you need differential equation like this, but both sides current should be there, but both sides current is not there. Here also both sides voltage is not there, so that is why what we have to do, you differentiate equation 2 with respect to z, then here dou square Vs by dou z square, then minus z into dou Is by dou z. Dou Is by dou z is in terms of voltage, then you get equation in which both sides voltage is there. So differentiate equation 2 with respect to z, then you get dou square Vs divided by dou z square is equal to minus z into dou Is by dou z, let us say this is equation number 5. So put equation 4 in 5. So dou square Vs divided by dou z square is equal to minus z into dou Is by dou z is minus y into Vs. So ultimately dou square Vs divided by dou z square is equal to z into y into Vs. So we will call this, we'll write one more step. So dou square Vs divided by dou z square is equal to, this is gamma square into Vs. I told you na, dou V square unity, dou square V unit is volt. This is also volt. Then dz is meter. Dz square means denominator meter square is there. So 1 by meter square. 1 by meter square is actually gamma square. You can see here also z is ohm per meter. This is mho per meter. Ohm mho cancel. Per meter into per meter. 1 by meter square. So that is gamma square. It is represented. Now almost you got, dear students. You got the equation of gamma. That gamma is a complex that is equal to alpha plus j beta. Alpha is attenuation constant, beta is phase shift constant. Then you are going to get the feeling that uniform plane wave concept and transmission line concept same. In uniform plane wave, electromagnetic power is carried using electric and magnetic field, and here in the transmission line, power is carried from source to load using voltage and current. Okay, so this one is equation number 6. So where gamma square is equal to z into y and gamma is equal to root zy. We will talk of that later on. We will write that in the note, no, separate note. So whatever is there in the box, you have to read those things. We will talk of this separately. Now what is z? R plus j omega l. What is y? G plus j omega c. Okay, let it be like that. Similarly, differentiate equation, this one, current equation. No. Where is that? Here, 4. Differentiate equation 4 with respect to z, both sides. Then dou square is divided by dou z square is equal to minus y into dou vs by dou z. So let us say this is 7. Now put second equation in place of dou vs by dou z minus zis. So put second equation in 7. Then you will get dou square is by dou z square is equal to minus y into, so dou vs by dou z is minus z into is. So ultimately you get z into y into is. So once again this equation, current equation, is similar to the gamma square. So it is similar to the voltage equation. So in the voltage equation, replace Vs with Is, then you get this equation. So that means solving one equation is more than enough, dear students. So in the uniform plane waves also you got dou square E excess divided by dou z square is equal to gamma square E excess you got, if you recall. So here also same thing. Once again here also gamma square is equal to zy and gamma is equal to root zy. So this is a voltage equation in phasor form. This is current equation in phasor form. So what was the heading? Heading क्या थे? Equivalent circuit of the transmission line and transmission line equations. So these are the equations, main equations. They are both similar. Okay. Now this heading is over. Now we will write one note. In that note we will be writing gamma square, otherwise gamma. So here gamma is equal to root zy. So gamma is equal to root of R plus j omega L and G plus j omega C, and ultimately unit is 1 by meter. So it is a complex, actually gamma is a complex. So this one is a complex. Complex into complex is complex, root of complex is complex. So every complex has a real and imaginary. So that gamma is a complex number that has real and imaginary. Okay, that real is called as alpha, and this is beta. Okay, where this gamma is equal to alpha plus j beta. Okay, now what is alpha? Previous chapter only, that is attenuation constant Nepper per meter. Then beta is a phase shift constant, otherwise wave number. So phase shift constant. Unit is radian per meter. What is gamma? Propagation constant. Wave propagation means how much attenuation is there, how much phase shift is there. If you tell how much attenuation is there, how much phase shift is there, that is called wave propagation. So this is a combination of both of them. That is why it is called propagation constant. So this gamma tells attenuation and phase shift. That means it tells propagation characteristics. That is why it is called propagation constant. So that is unit is 1 by meter. So here Nepper means no unit, radian means no unit. So this is also actually 1 by meter, 1 by meter, 1 by meter. But Nepper indicates that is a loss term. Radian indicates that is a phase term. That is the story of that. So students, in note second point is that characteristic impedance Z0 is capital Z by Y, because this is ohm per meter, mho per meter. Per meter cancel. Root of ohm square is ohm, and we will get this definition when we relate V and I. Later on I will derive and I will tell you later on. Till now in the equations we got gamma, but we did not get Z0. After some time I will be talking of voltage and current relation. There we will be getting Z0. Anyway, now I am writing in the continuation gamma and characteristic impedance. In the previous chapter they are like gamma and intrinsic impedance. Here it is characteristic impedance. So Z0 is equal to root of R plus j omega L divided by G plus j omega C. Actually the unit of this is ohm, that is why it is called impedance. Now this impedance is a function of 4 characters of the transmission line, so that is why it is called characteristic impedance. So Z0 is characteristic impedance of the transmission line. Okay, now next note I am writing. Till now student, you have remembered the voltage equation dou square Vs by dou Z square is equal to gamma square Vs. Current equation also similar. Then gamma is equal to root Zy and characteristic impedance is equal to root of Z divided by Y. Now let us write some more points. Note first point. If the conductors of the transmission line are perfect, then you know that R0, comma, medium is perfect dielectric, then G is equal to 0. Already we wrote this in the characters. So medium is perfect dielectric. So if the conductors of the transmission line is perfect and medium is perfect dielectric, then R0, G0 in this case. So gamma becomes 0 plus j omega L and 0 plus j omega C under root. Now what is gamma, dear students? Alpha plus j beta, that is equal to j omega into j omega under root j omega root LC. So you compare both sides. Then alpha 0, that means that is a lossless transmission line. That means in the transmission line, if you use perfect conductors and the perfect dielectric, then there are no losses. But this is ideal discussion. You cannot get perfect conductor and you cannot get perfect dielectric. It is ideal discussion. So beta is equal to omega root LC. Now have you seen this beta structure is similar to the uniform plane wave omega root mu epsilon. Already I have shown you in the static fields. Anyway, GATE students have not studied static fields. So I will show you that L into C is nothing but mu epsilon for the conducting structures. So omega root LC, otherwise you can see here L has mu, C has epsilon. So omega root mu epsilon. This discussion is also similar to uniform plane wave. Okay. Now in this case, characteristic impedance Z0 is equal to root of R is 0, 0 plus j omega L divided by 0 plus j omega C, that is nothing but root L by C, that is called as R0. Here R means real, not means characteristic impedance. So R0 is real characteristic impedance, actually this one. Okay, real characteristic impedance. Now is this discussion practical? No, this is not practical. Then practically in the note second point, if we select best conductor, then R is present, but very small. I wrote already. If we select best conductor and best dielectric, for best dielectric, G is present but very small. Then if we select best conductor and best dielectric, then R is not 0, so G is not 0. In this case, if frequency is high, that means the frequency of the signal which we are sending is high. In this case, if frequency is high, in such a way omega L is much greater than R, and omega c is much greater than g, then we can neglect r comma g. So what discussion is going on? Actually, gamma is equal to r plus j omega l and g plus j omega c under root. So what discussion is going on? For best dielectric and best conductor, r and g values are not 0, but what we are doing, we are increasing the frequency in such a way omega L product is much greater than R, so we can neglect R. Similarly, omega into C is much greater than G, so we can neglect G. So here neglect R comma G, then once again gamma is nothing but J omega root LC. If you neglect R and G, that means you leave them. Once again, you get this thing that implies here alpha is 0 and beta is omega root LC. Okay. Similarly, Z naught is equal to, you are neglecting anyway. I will write like this. Neglect R comma G in Z naught equation, then once again we get Z naught is equal to root of j omega L divided by j omega C, that is nothing but root L by C. We call that as a real characteristic impedance. Now I am asking one question, dear students, is this practical? Answer, this is also not practical, because already I told you, if frequency is very high in the transmission lines, then radiation starts. That is why this is also not practical. Then what is practical? Distortionless transmission is practical. We will write that in note 3. So distortionless transmission line. Actually, distortion means change of shape. Distortionless means there is no change of shape of the signal. That is the meaning of distortionless. Now, dear friends, for example, if R not 0, then G not 0, then alpha not 0, then loss is present. For example, this is a transmission line conductor. If we send here, testing is going on, like control systems, you do the testing with the impulse input, etc. For example, if I send here Gaussian signal like this, and output side also like this same is coming, output side also same is coming, in this case there is no change of shape, that means it is distortionless, and also no attenuation, so alpha is 0 for this. For example, there is a transmission line. If I send a Gaussian pulse, now the height is decreased, that means there is no change of shape, that means distortion is not there. So this is also distortionless. Because signal shape is not changed, but here amplitude is reduced, that means here loss is present, alpha is present, so it is a lossy transmission line. It is lossless as well as distortionless. Its loss is present but distortion is not there. No problem, we have amplifiers, we can amplify this and it works out. That is the distortionless transmission line. Alpha is present, loss is present, but signal shape is not changed. That is called distortionless transmission line. For example, any transmission line is there, and if I give the Gaussian pulse like this, then output side you got the signal like this. That means there is a change of shape here. So there is no use of this type of transmission line. Distortion is present. If signal shape is changed like this, and ultimately whatever information, whatever signal you send, same signal is not reaching the output side, so distortion is present. This type of transmission line not useful. Actually, we try to build a transmission line where alpha 0, that is lossless, and the signal shape is not changing, so this is distortion less. We need this type of transmission line, but unfortunately we have seen, if we select best conductor and best dielectric, R and G are present, so gamma is complex. If gamma is complex, alpha is present. So if alpha is present, loss is present, but at least we take care in such a way signal shape is not changed, so uh, distortion less is required. Now let us see what happens for distortionless transmission line. So dear students, distortionless transmission line. Actually, in the communication engineering, one definition is there. If any transmission structure like a two-way transmission line and what do you say, a coaxial cable, etc. If any transmission structure is to be distortionless, then attenuation constant alpha of that transmission structure should be constant. That means alpha should be independent of frequency, and phase shift constant beta must be linear function of frequency. That is the definition. Actually, I am writing the definition here. That is also objective question. If the transmission structure like two-wire transmission line, if the transmission structure is said to be distortionless, then attenuation constant alpha alpha then attenuation constant alpha must be constant or independent of otherwise independent of frequency, and phase shift constant beta must be linear function of frequency. Example, like this student, beta is equal to omega root mu epsilon. What is happening here? Beta is proportional to omega, so it is linear. Actually linear, like y is proportional to x, y is equal to mx type. This is okay. So if the transmission structure is said to be distortionless, then attenuation constant alpha must be constant. That means independent of frequency, that is, and phase shift constant beta must be linear function of frequency. So it should not be nonlinear, it should be linear function only. So this is the definition. Actually, I am putting this in the box, definition. Now what to do to satisfy this condition? By taking the general equation of the gamma. We will take general equation of the gamma, and we will try to get we will take one condition so that alpha and beta satisfies this condition. Now gamma is equal to r plus j omega l g plus j omega c. This is general equation of the gamma. Now what I do, I will pull out R from this. So 1 plus j omega L by R. Pull out G from this. 1 plus j omega C by G under root. This is gamma. If we design transmission line in such a way L by R is equal to C by G, that implies LG is equal to RC. I am putting this in the box. Then let us say this is equation number 2. If we design a transmission line in such a way this ratio equal, that means LG is equal to RC. You remember that here time constant is there. So LG is equal to RC condition is satisfied. If we design a transmission line in such a way this condition is satisfied, then what will happen? Let us see. What will happen? Let us see. क्या होगा उसके बाद हम लोग क्या किया, एक ट्रांसमिशन लाइन लिया, उसके बीच में डाइलेक्ट्रिक को चेंज करते गया, चेंज करने के बाद चेंज करते करते जब ये कंडीशन सेटिस्फाई हुआ उस समय में हम लोग वो डाइलेक्ट्रिक को यूज किया है. नाउ put equation 2, this is also equation 2, and this one both are same. Put equation 2 in 1 is this equation, then gamma is equal to R into G, then 1 plus j omega L by R, C by G is equal to L by R, so 1 plus j omega L by R whole square we get, root of. Now gamma is equal to root Rg and whole square is there, na? So this one, that is equal to root Rg plus j omega L by R root Rg. So ultimately root Rg plus j omega R cancel, dear students. So you get okay, L multiplied with root G by R, this one gamma. So let us say this is equation number 3. Now from this condition, equation 2 implies, from this equation now you send this G here, G by R is equal to C by L, G by R is equal to C by L. This I wrote from equation 2 only. So put 4 in 3, then actually what is the student? Gamma. Gamma is alpha plus j beta, that is equal to root Rg and j omega L, and root G by R is nothing but root C by L. Okay, root C by L. Now what is this? This is equal to root Rg plus j omega. Here na it goes inside root of L square, so that LL cancel, root LC you get. So alpha plus j beta. Compare both sides. Compare both sides. So you get alpha is equal to root Rg. It is not a function of frequency. So actually it is constant. It is constant. And beta is equal to omega root LC. So that implies beta is proportional to omega. It is a linear function of frequency. So that is why, dear students, now whenever you design a transmission line in such a way this condition is satisfied, then alpha becomes constant and beta is a linear function of frequency. So this alpha and beta satisfy the distortionless condition. Okay, that is why this is called condition to have a distortionless transmission? That is also one of the objective question. So, right here, let us say this is 5 and this is 6. Equation 5 comma 6 satisfy the definition of distortionless transmission line. Okay. So, LG is equal to RC is called as condition to have a distortionless transmission. Condition to have a distortionless transmission. Okay. Now, I will write one more note by linking distortionless and lossless transmission line. Here I will write note like this. First one, if R is equal to R0 comma G0, second one, R not 0, G not 0, but omega L is much greater than R and omega C is much greater than G, then for this case also, for both the cases you got alpha 0 and beta is equal to omega root LC you got. So both are actually lossless cases. They are lossless because alpha is 0. These are note 1 and previous note 1 and note 2. Here na R present, G present, but they are less. If we increase the frequency, then omega L much greater than R, omega C much greater than G, then alpha becomes 0, beta is omega root LC. They are lossless because alpha is 0. Third one, if LG is equal to RC, condition is satisfied. If LG is equal to RC, condition is satisfied. Here also R not 0, G not 0. Then what happens in the transmission line? Alpha is equal to root RG and beta is equal to omega root LC. So here alpha is constant but loss is present. So this is also distortionless because alpha is actually, it is a constant, no students, it is constant. So this is distortionless transmission line because alpha is constant, beta is proportional to omega. So it is distortionless. Now this is also distortionless. This is also distortionless. Why? For lossless transmission line, alpha 0 is constant actually. It is not a function of frequency. And beta proportional to omega, it is linear function of frequency. So that is why lossless transmission line satisfies the definition of distortionless. Because for lossless transmission line, alpha constant, beta proportional to omega. So lossless line is also distortionless transmission line. Now you see this one, this is distortionless transmission line, but here alpha not 0 means loss is there. So distortionless transmission line, this one, but distortionless transmission line does not guarantee the lossless. Loss may be present, loss may not be present. So once again I am repeating here, these two give lossless transmission line, and if a transmission line satisfies this condition, that is distortionless actually. So this is distortionless, and both are distortion, both satisfy the distortionless condition. So that is why I told lossless line behaves like a distortionless line, but distortionless line does not mean lossless, because alpha not 0. So here I am writing lossless transmission line is also a distortionless transmission line. Distortionless transmission line does not mean a lossless transmission line. This is also, they say, distortionless transmission line does not guarantee a lossless. That means distortionless transmission line does not mean a lossless, because this is also distortionless. I wrote here, this is also distortionless, this is also distortionless, but this has loss because alpha not 0. So this is the one note actually. Okay. Now one more note, student, I am writing here. General equations of gamma. So this is Z naught, characteristic impedance. Gamma general equation is R plus j omega L G plus j omega C under root. Now Z naught is equal to root of R plus j omega L divided by G plus j omega C. General means we are not taking any conditions. This is general equations they are. Now lossless transmission line. That means you know that lossless transmission line means maybe this case or maybe this case, any one of the case. Lossless transmission line. Then for that gamma is equal to j omega root LC. In this case alpha 0, beta is equal to omega root LC. This is nothing but j beta. Gamma is purely imaginary, then there is no loss. Then Z naught is equal to root L by C, that is real characteristic impedance. Then distortionless transmission line. For this alpha is gamma is equal to root Rg plus j omega root Lc. Here alpha is root Rg and beta is equal to omega root Lc. Now once again here Z naught is equal to root L by C. If you want, you can see here Z naught is equal to R plus j omega L. R you pull out 1 plus j omega L by R. So G you pull out 1 plus j omega C by G. Now distortionless condition is what, student? Distortionless condition, Lg is equal to Rc. That means okay, I will do one thing. From this I will calculate R by G ratio. Na? R by G is equal to L by C. Okay, and L by R is equal to C by G. So this one and this one cancel. So Z naught is equal to root R by G you get. Once again from this R by G is equal to L by C. That is nothing but L by C. So this one, just that is rough work actually. For distortionless transmission LG is equal to RC, and this is also rough work actually. Okay, students. So conclusion is that for lossless transmission line, Z naught equation, for distortionless transmission line, Z naught equation, they are real. Okay, right. So dear friends, now in general, common transmission line means transmission lines which we use coaxial cable. Coaxial cable means the central conductor. Here conductor characteristics, no? Sigma C. Sigma means conductivity of the conductor. Mu is permeability of the conductor. Epsilon permittivity. C means of the conductor. Generally for conductor permittivity is equal to epsilon naught only, because epsilon is 1 for the conductor. And in between the conductors, here dielectric medium is present. For that dielectric medium conductivity is sigma, mu and epsilon. Suffix C is there. They are conductor parameters actually. Okay, this is epsilon naught. Okay, now the inner conductor radius is A, outer conductor inner radius is B, outer conductor inner radius is B, outer conductor outer radius is C. So two conductors are there. This is first conductor, this is second conductor. I told you if we connect voltage here between them, then current goes in the inner conductor, again comes back through the outer conductor. Similarly here also like that, two-wire transmission line, first conductor, second conductor, and if we connect the voltage here, in this conductor current goes, then supplies to the load here, again comes back. So here A is radius of the conductor, this one radius of the conductor, and D is the distance between centers of the conductor here. So here A is inner conductor radius, B is inner radius of outer conductor, C is outer radius of outer conductor. So this is called outer conductor. This is called inner radius of the outer conductor. This is called outer radius of the outer conductor. So here A is radius of conductor and D is distance between centers of the conductors. Here medium is present. Now what is the meaning of planar line or otherwise planar transmission line? Here you take one dielectric like this, and this bottom side, this sponge is there. In place of sponge you take conductor sheet like this, bottom side conductor sheet. Top side also similar to this sponge here, one conductor sheet is there like this. So the conductor sheet is there. What is the thickness of that conductor sheet? T. And this dielectric is there here of D height, width W, dielectric is there here. So this is called planar transmission line, or otherwise planar two-way transmission line. Here top side also conductor sheet, bottom side also conductor sheet. Thickness is T for conductor and dielectric is there here. Now width of the conductor is W and D is the, of course, width of the conductor as well as the dielectric both are W, and D is the height of the dielectric actually. T is the thickness of the conductor sheet actually. Now for these parameters, if you do the derivations, the parameters RLGC for each transmission line becomes for coaxial cable, these are the this is the resistance, this is the inductance. Already we have solved this in the static fields also, and C is this one, 2 pi epsilon h ln b by a. Per meter length you are taking h is equal to 1. So Here I already told you, dear students, sigma means what? That is conductivity of the medium. That is the conductivity of the medium present between the conductors. Be careful in the notations, symbols here. Okay. For example, now students, resistance is calculated for the conductors actually. That is why here sigma of the conductor came. You must be careful. And also I told you G and C are calculated for the medium present between the conductors. That is why the sigma is conductivity of the medium and this is epsilon is permittivity of the medium. I wrote here medium characteristics they are. So this R and C anyway, resistance is series resistance. You can see here conductivity of the conductor. Here also conductivity of the conductor should be there. It depends on your patience whether you remember these formulas or not. That is up to you. Anyway, wherever conductor comes, na, for conductors, skin depth is equal to del is equal to 1 by root of pi f mu of the conductor and sigma of the conductor, student. Mu of the conductor, because skin depth is calculated for conductor 1 by root of pi of mu sigma. So mu of conductor, sigma of the conductor. I am telling you, if you want, you can write there. Okay. So here del formula is there, na? Here also del is there. Here also del is there. The del formula is that is skin depth actually. So 1 by root pi of mu sigma, that is for conductor. So mu of the conductor multiplied with the sigma of the conductor. Already we have seen in last chapter del is 1 by root pi of mu sigma. That is one thing. And also if d by 2a whole square is much greater than 1, then this cos h inverse of d by 2a becomes ln d by a, it becomes base e. So in above formulas, this is one discussion, this is one formula written. So in above formulas here, na, in above formulas, if d by 2a whole square is much greater than 1, then cos h inverse of d by 2a becomes ln d by a. Okay. So now I am taking here one observation. Otherwise, you can write this as observation I am writing, but anything comes in the box, you have to remember that one. For coaxial cable, I will take lossless coaxial cable. For lossless coaxial cable, resistance is 0 and G also 0, and L becomes here you can see L, student, mu by 2 pi ln b by a. So mu by 2 pi ln b by a. C becomes 2 pi epsilon. Here it is 2 pi epsilon ln b by a. So 2 pi epsilon ln b by a. And for lossless coaxial cable, R0, G0, L is this one, C is this one, and we have already derived Z0 is root L by C. That means root of L is this one, mu by 2 pi ln b by a divided by C is 2 pi epsilon divided by ln b by a. So that is equal to here you get 1 by 2 pi root mu by epsilon, and this goes here So ln b by a, because root of ln b by a whole square. Ultimately, this is equal to 1 by 2 pi, and root mu by epsilon is eta naught, root mu naught by epsilon naught, that is 120 pi root mu r by epsilon r ln b by a. This cancel, you get 60. And for dielectrics, this is actually mu means for dielectric medium. For dielectric, mu r is 1. So for, I told no student, here mu and epsilon, they are the parameters for the medium actually. Okay. For dielectric, mu r is equal to 1. So now z naught is equal to root L by C, that is equal to 60 divided by root epsilon r ln b by a base E ohms. So this pi cancel 60 and ln b by a. This is the formula of the characteristic impedance of lossless coaxial cable, and 60 by root epsilon r. Root epsilon r is a relative permittivity of the medium between the conductors. Okay, if you want, I will write this is the characteristic impedance. A is inner conductor radius. Okay, B is inner radius of outer conductor. Okay, next epsilon r is relative permittivity of the medium present between conductors. So dear students, similarly, if you calculate the characteristic impedance of the lossless two-wire transmission line, now by taking this in place of cos h inverse d by 2a, by taking ln d by a, so you get a similar formula, but in place of 60 you get 120 by root of epsilon r ln b by a, ln d by a you get. So I will write that there. So what I am telling you is that actually here I wrote the structure and parameters. Here there are the formulas for them. So coaxial cable here written, for two-way transmission line parameters are written here. For planar transmission line, line means transmission line, line means transmission line. Planar means the conductor surface are looking like a sheet or otherwise plane. For planar transmission line, here parameters are written. They came from derivation, students. Okay. Now for lossless, similarly note for lossless two-wire transmission line, Z naught is equal to root L by C is equal to 120 divided by root epsilon r ln d by a, of course base E ohm. Ln means base E, log means log, log means base 10. Okay. So here A is radius of the conductor and D is distance between centers of the, D is distance between the centers of the conductors in the diagram already shown. So epsilon r is a relative permittivity of the medium present between the conductors. So epsilon r is the relative permittivity of the medium present between the conductors. Okay. Now in the note we will write point phase velocity is equal to omega by beta, omega by omega root LC, that is equal to 1 by root LC. For example, for coaxial cable, if you see, for coaxial cable, this is L and this is C. You multiply L into C, what will happen? You get mu epsilon. So that is why 1 by root LC is also equal to 1 by root mu epsilon. So that's what we got in the uniform plane wave. Okay. So that phase velocity is nothing but C by root mu r epsilon r also comes. So that is also applicable here. So here mu r is permeability of the relative permeability of the medium. Epsilon r is relative permittivity of the medium between the conductors. Okay, and here also that formula lambda is equal to 2 pi by beta is applicable. So 2 pi divided by beta is omega root LC here, same formula. So here beta into Z, that is beta is nothing but 2 pi by lambda into Z is this is both are equal. This is this one. Beta Z is called as electrical length of the transmission line. So electrical length of the transmission line, beta Z is called as electrical length of transmission line, because later on we will see beta into Z decides the impedance of the transmission line. Impedance is electrical parameter, so that is why this is called as electrical length of the transmission line. So in some questions they ask you, by giving the length of the transmission line, they ask you to calculate the electrical length, then beta into Z is length of the transmission line here. So where beta is 2 pi by lambda. So later on we will discuss Z is given in terms of lambdas, actually lambda by 2 transmission line, lambda by 4 transmission line, lambda by 8 transmission line, like that. We will discuss that later on. So these are the points, dear students, in the note.